Good morning, ma'am. Myself, Gauri Kulkarni. So, in this video, we are going to explain about uh, bucket sort, radix sort, and Fibonacci leaf. So, uh, now I'm going to explain about bucket sorting. So, bucket sort is a sorting technique where elements are divided into different groups called buckets and sorted individually and then combined back together. It works best with when data is uniformly distributed. So, it is a linear time sorting. So here it distributes the elements into number of buckets and sorts the each bucket individually, then concatenates. The time complexity is order of n plus k, and the worst is order of n square, and space complexity is order of n plus k. So it is a stable sort. Relative order of equal elements is preserved, and it is commonly used when with floating point numbers. So it creates the algorithm is it creates the n empty buckets, usually n equals to size of the input array, and insert each element into bucket, and then sort each non-empty bucket using insertion sort, and then concatenate all buckets in order to get the sorted array. So in today's example, we have got 10 elements, which is having index of 9 from 0 to 9. The elements are 0.78, 0.17, 0.39, 0.26, 0.72, and so on up to 0.68. So we will create 10 buckets and 10 empty buckets from B of 0 to B of 9. And then the rule is we have to multiply 10 into the element. So now 10 into 0.78 equals to, it will get 7. So we will put that number in B of 7 bucket, and then 10 into 0.17 equals to B of 1. And again here 10 into 0.39 equals to B of 3. So by doing here, we will add each element into number of buckets. And by adding that, in this bucket B of 0 there are no elements, and in B of 1 we have got two elements, that is 0.17 and 0.12, and here in case of B of 2 as well we have got three elements, that is 0.26, 0.21 and 0.23, and in B of 3 we have got one element 0.39, and B of 4 is empty, B of 5 is also empty, and in B of 6 we have got 0.68, and B of 7 having 0.78 and 0.72, and B of 8 is empty again, and B of 9 we have 0.94 element. So by doing this, in one bucket we have more than one element, so we have to sort it by using insertion sort or any other sorting techniques. So in this I'm using insertion sort, which is very easy to implement. So in B of 1 we have got two elements, so we will sort it by minimum value as first. So first one is 0.12 and then 0.17, and again in B of 2 as well we will sort, and then in B of 3 also we will sort, and the final sorted array is 0.12, 0.17, 0.21, 0.23 and up to so on. And the advantages of bucket sort is it is very fast for uniform data. If numbers are evenly distributed, bucket sort can run in nearly. So it having time complexity of order of n, which is faster than many comparison sorts, and it is very easy to understand because the concept is very simple. Like in that we have to only divide into buckets, sort each bucket and merge the buckets, and it is good for floating point numbers as well, and then it can be parallelized, like different buckets can be sorted at the same time using multiple processors. And disadvantages of bucket sort is it is not good for even uneven distribution. If many elements fail into one bucket, the performance becomes poor. So the worst case time complexity is order of n square, and then extra memory required because needs additional space for creating the buckets, and choosing the bucket is very difficult. Like performance depends heavily on number of buckets, bucket size and data distribution, and it is not suitable for very large range of data. And the application of bucket sorts are like sorting floating point numbers, distributed data processing, database system, and then parallel computing, histogram and data analysis. and etc. And the next topic will be continued by Anjali. Thank you.
I'm Anjali. Now I am going to explain about radix sort. Radix sort is non-comparative sorting algorithm. This sorts integer digit by digit from least significant digit to most significant digit. Time complexity is order of t into n plus b, where d is equals to digits and b is equals to base. Usually it's 10. And it is non-comparative sort, never directly compares two elements. First algorithm of radix sort is first step one, find the maximum element to determine number of digits for each digit position, ones, tens and hundreds. Like counting sorts on digit at position p. Array is now sorted with respect to digit up to position p. After processing all digits position, the array is fully sorted. Now I'm going to explain about the example. We are taking input array which are 8 elements is 170, 45, 75, 90, 802, 24, 2 and 66. And here the maximum element is 802, which is 3 digit. First we have to sort in 3 phases. Pass 1 in unit digit, in pass 2 in tens digit, in pass 3 100 digits. In pass 1, we have to sort the input array by units digit. In 0th index, we are assigning 170 and 90. In second digit, in second index, we are assigning 802 and 2. In fourth index, we are assigning 24. In fifth index, we are assigning 45 and 75. And in sixth index, we are assigning 66. And in 1, 7, 8, 9, and 3, we are keeping it empty. This is the sorted array of pass 1, which is sorted by units, which is 170, 90, 802, 2, 24, 45, 75, and 66. And we have to repeat the same process for sorting this element array by tens and by hundreds, and we'll get the final array, sorted array after sorting by hundreds, which is 2, 24, 45, 66, 75, 90, 170 and 802. Thank you.
Hello, I am Anushri and my topic is Fibonacci heap operations. A Fibonacci heap is an advanced priority queue data structure made of multiple heap ordered trees, and it is efficient because most operations work in constant amortized time. So the first operation is Fibonacci heap insert operation, where in insert operation a new node is created and directly added to the root list of the heap. For example, when we insert in elements like 3, 7, 21, 52, 38, 17 and 24, each node is simply attached to the root list. No rearrangement or consolidation happens during insertion. The minimum pointer is updated whenever a smaller element is inserted. Here the minimum becomes 3, so the insertion is very fast and takes O of 1 amortized time. And then find minimum. In find minimum operation, we simply return the node pointed by the minimum pointer. Since the heap always maintains a pointer to the smallest element, no traversal is required. In this example, the min pointer points to 3, so find min returns 3. Its time complexity is O of 1. Union. In union operation, we use two more. In union operation is used to merge two Fibonacci heaps. We con concatenate the root lists of both heaps using pointer manipulation. For example, heap A has minimum 3 and heap B has minimum 17. After merging both root lists, we compare the two minimum pointers and keep the smaller one, which is 3. No node copying or restructuring happens, so union also works in O of one time. Thus, Fibonacci heaps achieves very efficient operations because it postpones complex restructuring work until necessary. That is why operations like insert, find minimum, and union are extremely fast.
Now I'll explain two important operations in Fibonacci heap, that is extract minimum and decrease key. These operations make Fibonacci heap very efficient for priority queue operations. So first let's see extract minimum. In extract minimum, we remove the smallest element from the heap because Fibonacci heap always maintains a pointer to the minimum node. Now, first the minimum node is removed from the root list and then all its children are added directly to the root list. After that, the consolidation is performed and in consolidation, trees having the same degree are merged together so that the heap becomes original organized again. So here, as you can see, there are three nodes and the minimum here is the node with the three element. So we delete that from the root node and all the other children nodes are merged together and they are merged in a way so that the heap becomes organized and in correctly ordered degree. And the time complexity of this is O log of n. Next, let us see decrease key. In decrease key, we reduce the value of a node key. This operation is useful when a nodes get higher priority. First, the node value is updated. Then, if new node value becomes smaller than its parent, then the minimum heap property is violated. So, the node is cut from the parent and moved to the root list. If the parent was already marked, then the cascading cut happens upward recursively. Finally, the minimum pointer is updated if needed. Here, the minimum pointer is updated as per the decreased key. So let us see the visual example of how the decreased key works. Here, the key 52 is decreased to 5. Since 5 is smaller than its parent, the node is cut and moved to the root list. Now 5 become the new minimum node. And the time complexity of the decrease key is O of n, which is the biggest advantage of the Fibonacci heap. So because of fast decrease key and efficient extract minimum operation, Fibonacci heaps are widely used in algorithms like the Dijkstra and Prim's algorithm. So that sums up our presentation of Fibonacci heap, bucket sort and radix sort. Thank you.